Covalent bonding. Covalent bonding. What does this occur between? This occurs between non-metals. Just non-metals. What makes a non-metal a non-metal? What makes a non-metal a non-metal is its tendency to gain electrons. So, we're looking at a type of bonding where everything is looking to gain electrons. It is energetically favourable for every atom involved in the bonding to gain electrons. How can everything gain and nothing lose? Well, the only way for that to happen, I'm just going to write a keyword across the top, is sharing. And we'll come back to this keyword time and time again in this video. This video is all about sharing. I'm actually not going to write the definition in straight away. I'm going to draw some examples, and from those examples, hopefully, we can get to looking at the definition. So, hydrogen chloride. You need to know that the formula for hydrogen chloride is HCl. Hydrogen has an electronic configuration of 1, and chlorine has an electronic configuration of 2, 8, 7. Now, we are going to do all of these diagrams drawing only the outer shells, because 99 times out of 100, that is how you are asked to do it at GCSE and even at A level, to be honest. So we're going to draw showing just the outer shell. So we're interested in the 1 for the hydrogen and the 7 for the chlorine. So very quickly, hydrogen, drawing just an outer shell, there's going to be a 1 electron in it. Chlorine, which we generally draw bigger because it is. Hydrogen we always draw smaller because it is the smallest. Chlorine is going to be 1, 2, 3, 4, 5, 6, 7 if we're just drawing the outer shells. Okay, so let's have a quick look. Both are looking to gain because it's energetically favourable to do so, and both will end up with full outer shells. If we have a quick look with a highlighter, we can see that there is a gap here where an extra electron can fit into that shell. There is a gap here where an extra electron can fit into that shell. How does this work? Well, if we share this electron and that electron, I'll show you how in a minute, we will end up with both species having effectively gained electrons, and therefore we have completed that energetically favourable process, which is non-metals gaining electrons. Let's see what this looks like when we draw it out. So I've brought the two species together. Their outer shells are overlapping to show that they are going to be sharing electrons. Okay. Where are the electrons going to be shared? Well, there is a pair of electrons being shared there. Those electrons are, let's just highlight them up here, this electron here from the hydrogen, which is the cross, this electron here from the from the chlorine, which is a circle. Did hydrogen have any other outer shell electrons? No, it didn't. It only had 1, and I've drawn in 1 cross. That's done. For chlorine, I've drawn in 1 circle. However, there were originally 7 circles, so I need to draw in 6 more. 1, 2, 3, 4, 5, 6. Done. That is hydrogen chloride. So, what's happened? We have shared a pair of electrons between the two atoms. Those electrons are sitting between the nuclei, which is what these letters are representing. H for a hydrogen nucleus, Cl for a chlorine nucleus. Nuclei having only protons and neutrons in them are going to be positive. The electrons in the middle, the shared pair of electrons being negative, those things are oppositely charged. Positive nuclei, negative pairs of electrons. So let's have a look at the definition. Definition of covalent bonding. As with all bonding, it is an electrostatic force of attraction between or acting between. And what's it acting between now? The shared pair of electrons. That's the bit in yellow in the diagram. And it's very important, you have the full thing, otherwise it makes no sense and doesn't work. And the nuclei, plural, of both atoms. And those are the things that I highlighted for you in green. So there you go. The electrostatic force of attraction acting between the shared pair of electrons and the nuclei of both atoms. Why a shared pair? Sharing. These are non-metals. Energetically, it is favourable for them to gain electrons. The only way everything can be seen to be gaining is by, and we'll go back to that keyword we had at the top, by sharing the electrons. And we always share electrons. What are we sharing? Electrons. So, and we always share electrons shared in pairs. It's always important. If you have a crossing over bit and you have an odd number of electrons in it, you've probably done it wrong, or you've almost certainly done it wrong, at GCSE anyway. So, let's run through a few more examples. Pardon me. Right, so water. Hopefully you all know that water has a formula of H2O. Let's see why. Okay, hydrogen we already know has an electronic configuration of 1. Oxygen is 2, 6. 2, 6. 6, 7, 8. There are going to be 2 gaps in the outer shell, effectively in the outer shell of oxygen, which means that it will need to form 2 covalent bonds to get up to that full outer shell so that everything is gaining electrons. What is that going to look like? I'll draw you the diagram now. Okay, so it's just popped up for you. We have 2 H's. As I said, we always draw the H's a bit smaller, and 1 O. The O has to go in the middle because it is making the 2 bonds. The H's have to go on the outside because they can only make 1 bond each. Because they can only make 1 bond, H's always have to go on the outside. At least this is certainly true for GCSE and A level. Okay, so let's look at putting the electrons in. We're going to have a bond here. That's 1 shared pair of electrons. So we're going to have a bond here. That's 1 shared pair of electrons. Hydrogen brought 1 electron in its outer shell, and I've drawn 1 cross for the left-hand hydrogen and 1 cross for the right-hand hydrogen. So there are no more electrons to draw in for the hydrogens. Oxygen brought 6 outer shell electrons. How many open circles have I drawn so far? 1, 2, which means I have 4 left to draw in. 4, 3, 2, 1. Let's just get a highlighter and check this. 2, 6, so I should have 6 circles in total. 1, 2, 3, 4, 5, 6. Absolutely. And if I just count these 2 crosses as well, that makes it seem that oxygen has those 8 outer shell electrons, that full outer shell, which is good. Hopefully, as I just said, you can now see why water is H2O. If we had only used 1 H, there would be only 7 outer shell electrons round that oxygen at the moment, and that wouldn't work. If we had used 3 H's, we would have 9 electrons round that outer shell of the oxygen, and that wouldn't work. So it's got to be H2O. It is what it is. Okay, 2 more examples, and what I'm going to do is I'm actually just going to draw these ones in for you and then talk them over. Firstly, ammonia. 3 hydrogens bonded, so 3 bonding pairs, 1 bonding pair, 2 bonding pairs, 3 bonding pairs. The hydrogens only brought 1 electron, so they are already done. We've seen that in the previous examples. And the nitrogen brought 5 electrons. We've drawn in 1, 2, 3 of them for those circles. So we have one, what we call a lone pair left. 1, 2. 1 lone pair, 2 electrons. Done. Now, last one. I've written down ethane, but actually, I'm going to do a different example. I'm going to do something called ethene. Why am I going to do ethene? Well, ethane has a formula of C2H6. That is ethane with an A. You'll learn more about this in organic chemistry later. But ethene with an E is C2H4. Ethene. And for this to work, we must have something called a double bond. And it probably serves to have one example with a double bond. And we'll see why. So this is C2H4. Carbon is 2, 4. Hydrogen is just the 1. Carbon being 2, 4 is going to have 4 bonds. Okay, 4 bonds. But if we have a quick look at our formula, C2H4, let's just put this one in brackets because we're in a box, so we're not going to use it. C2H4, how's that going to work? Well, I'm going to introduce something called a line diagram here. Let's just show what a line diagram for water would be. Line diagram for water, I'm sure you've seen before. Oxygen in the middle, a line to a hydrogen, a line to a hydrogen. The line equals the shared pair of electrons. That's a line diagram or a display formula. What's that going to look like for ethene? Well, we know the hydrogens have to go on the outside because they can only make 1 bond. So we have a carbon and another carbon. They can link together. And we have 4 hydrogens, so it makes sense to put 1 hydrogen there, 1 there. So we've got a pair of hydrogens on there and a pair of hydrogens on there. How many bonds did a carbon need to make? Well, it was 2, 4. A carbon needed to make 4 bonds. Our carbons have only made 3 bonds. How can I get a 4th bond? Well, I could bond to another hydrogen, but I don't have any more hydrogens. I've only got 4 hydrogens, and I've accounted for all 4 of them. So I can't chuck in extra hydrogens, because if I did, I'd end up with 6, and that would be ethane, and that would be a completely different compound, which is not what I'm trying to draw. So, how can the carbons have more bonds? They're going to form 4 bonds because it's energetically favourable for them to do so. And the only way we can do that is by having a double bond. And we draw an extra line in there. So each line represents a shared pair of electrons. So with this diagram, between the carbons here, I have a double bond, which is 2 shared pairs of electrons. So let's just draw that and see what it looks like as a dot and cross diagram. Okay, so it's just popped up where all of the circles are, so let's put in the pairs of electrons. So between carbon and hydrogen, we have a shared pair. Between carbon and hydrogen, we have a shared pair. Between carbon and the carbon on the right and the hydrogens on the right, we have a shared pair. Let's just draw the circle as a closed-in circle, and I'll show you for why in a second. Cross and a closed-in circle. So the crosses are the electrons that came from the hydrogens. The open circles are the electrons that came from the left-hand carbon, and the closed circles are the ones that came from the right-hand carbon. We have, if I can just find a highlighter, already discussed that we need a double bond, i.e. 2 shared pairs of electrons in the middle. So what's that going to look like? Well, 1 shared pair, the open circle coming from the left-hand carbon, the closed circle coming from the right, and the second shared pair. Let's just do a quick count up. Carbons, well no, let's do the hydrogens first. Hydrogens brought 1 electron each. I have, for each hydrogen, 1 cross, so there's no more to do, no more to put in. Carbon's brought 4 outer shell electrons each. The left-hand carbon, let's just use a highlighter to highlight over the top. I have 1, 2, 3, 4 open circles. That's grand. No more need to be put in. There are no lone pairs for that carbon. And it's symmetrical, so you can probably already see what's happened. But let's do it anyway. For the right-hand carbon, I've got 1, 2, 3, 4 filled in circles. That is all of the 4 outer shell electrons that the carbon brought along. So there we go. That is ethene with an E. It is a member of the homologous series called the alkenes, something you will learn about later, or if you're looking at this as revision, you should already know about. Why did I change the example to do ethene? Because ethene needed the double bond. So this is an example of a double bond. Again, though, we are still looking at shared pairs of electrons sitting between the nuclei of 2 atoms, the definition of the covalent bond being the electrostatic force of attraction between the shared pair of electrons and the nuclei of both atoms. Why are we sharing? Because we are dealing with non-metals. Non-metals are defined really as non-metals by their tendency to gain electrons because it's energetically favourable for them to do so. And how does everything gain? Well, that takes us right back to the top. The only way everything can gain is if we share. And the sharing here is the sharing of electrons in pairs. So that is covalent bonding. As always, go and do extra examples. Go and look through your notes. Go and make revision notes and get your head round covalent bonding.